Okay. I now call to order the Society's 2,424th meeting in the 149th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests and friends to tonight's lecture by Charles Clark. Tonight is the Society's annual meeting, and I am to give you a short report on the state of the Society. I am pleased to report that the Society did quite well in the last fiscal year, up to the end of in-person meetings, and then with the last 3 meetings of the year using Zoom. Financial support was adequate to meet expenses. Reserves continued to grow. Attendance at dinner and lectures grew slightly over last year. There are now 144 videos on YouTube and Vimeo, and viewings on YouTube are approaching 500,000. Social media subscribership continued to grow. The Society is looking forward to continued growth in the coming year, increasing its capacity to utilize projective and participatory technologies like Zoom, and to some new programming initiatives. The finances were audited and found to be sound and without objection. A copy of the Audit Committee report and a financial report are available by request to the corresponding secretary at correspondingsec@pswscience.org. The Society is grateful to the sponsors of the 2020-2021 lecture series for their support. The Policy Studies Organization, in cooperation with the American Public University, and a generous donor who asked to remain anonymous. I'm pleased to announce the following new members: Marisa Conlin, an attorney and a patent examiner in the USPTO, interested in physics, astronomy, and environmental science, who found PSW through the internet. Sue Powell, a student at Grand Canyon University, interested in mathematics and physics, who found PSW through the PSW Science YouTube channel. Michael Halpern, a molecular epidemiologist at the National Cancer Institute, interested in health services research, health economics, and the history of medicine, who comes to PSW through PSW's lecture series. And tonight's speaker, Charles Clark, whose interests will be clear in some small part from tonight's proceedings. We welcome them to membership. If you're not a member and would like to support the Society, you can do so through the PSW website. We welcome new members. Recording Secretary James Heelan will now read the minutes of the 2,423rd meeting and the lecture by Henrik Christensen. James, the screen is yours.
Thank you, Larry. Good evening, everyone. On June 26, 2020, by Zoom video conference broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2,423rd meeting of the Society to order at 8:03 p.m. Eastern Daylight Time. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The recording secretary then read the minutes of the previous meeting. President Milstein introduced the speaker for the evening, Henrik I. Christensen, Professor of Engineering and Director of the Contextual Robotics Institute at the University of California at San Diego. His lecture was titled Contextual Robotics, Making Intelligent Robots That Serve Society. Christensen's work addresses how robots can empower people in their everyday lives. Increasingly, people desire to purchase individualized products. The world's population is also both aging and urbanizing. These shifts are growing demand for robotics. Technological advances in creating smaller, more powerful electronics are making it possible for robotics to operate in previously inaccessible contexts. Together, these developments are causing corporations to evolve from their traditional strategies. Demand for customized products has kept humans involved in manufacturing processes. However, advances in sensor technology are improving robotic abilities to increasingly replace human involvement in non-uniform manufacturing, agriculture, distribution, and medical processes. The novel coronavirus pandemic has further escalated demand for robotics to perform work that minimizes physical human-to-human contact. Christensen addressed the current generation of commercially available companion robots. He said, most of these robots fail because they are insufficiently robust, for example, by limitations in current battery technology, or they lack the sophistication required to effectively navigate their environments. He also said that while modern homes may vary in design, their layouts vary relatively little compared to other structures and to outdoor environments. And aging populations demand robotics to aid them in maintaining autonomy. It is unsurprising then, Christensen said, that robotics intended to replace simple human tasks with limited environmental variations, like home vacuuming, have succeeded. Christensen predicts home robotics will continue to facilitate robotic advances. In a post-COVID world where humans will be less inclined to touch robotics to instruct them, Christensen said that one of the next frontiers will be operating robotics in varying social contexts, which change the meaning of words and symbols. One step toward that goal is improving biometrics, for example, by understanding human affective states through improved facial and body tracking. Christensen lastly discussed next-generation transportation. In 2016, the average moving speed in London was 5 miles per hour slower than it was in 1916 when people traveled by horse and buggy. Pre-pandemic, increasing urbanization increased congestion, which in turn increased people's average commute times. Manufacturing faster cars is not the solution, Christensen said. Rather, entire transportation systems must be overhauled to maximize autonomous travel. Because humans travel all over the world, fully autonomous transportation would need to navigate virtually unlimited contextual variations. Researchers at UC San Diego have begun modeling those variations and experimenting with autonomous mail delivery vehicles equipped with a suite of sensors, including 6 cameras and LiDAR. The researchers are currently working on anticipating actions, such as whether a pedestrian will cross the street. Long-term evaluation will be essential to success. Christensen then answered questions from the viewing audience. One member asked about data governance to protect user privacy. Christensen said researchers are working to reduce the amount of novel information transmitted from robots. For example, the UC San Diego autonomous mail vehicles substitute pedestrian faces with fakes. A member viewing from Australia asked about variable latency and bandwidth considerations for robotics in space. Christensen said, the German Aerospace Center, or DLR, is working to leverage more powerful ground-based computing to run simulations and communicate predictions to space-based robotics in a model-based approach to the problem. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:45 p.m., President Milstein adjourned the meeting. The temperature here in Washington, D.C. was 31 degrees Celsius. The weather was partly cloudy. And viewing through the live stream on Zoom were 28 attendees. And on the PSW Science YouTube channel, 38 attendees. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Minutes will be posted to the website. Please send any corrections or comments on the minutes to corresponding secretary Robin Taylor at correspondingsec@pswscience.org. We now turn to tonight's lecture on vortices of light and matter waves. And it's my pleasure to introduce tonight's speaker, Charles Clark. Charles is a fellow at the National Institute of Standards and Technology and a fellow at the Joint Quantum Institute of NIST and the University of Maryland. Previously, he was co-director of the JQI. Charles works on basic and applied problems of atomic, molecular, optical, and neutron physics, and he has a keen interest in vision systems in organisms. He earned his BA in mathematics and physics at Western Washington State, and his SM and PhD at the University of Chicago. All questions will be fielded after the lecture during the Q&A session. Charles, the screen is yours. Charles?
There, now I've got to start my video briefly, and that's another big challenge. Well, thank you very much, Larry. It's a real honor to be able to join this audience tonight. And let me just, without further ado, get started with my story. Annotate. So yes, my name is Charles Clark. I'm a member of staff, career civil servant at the National Institute of Standards and Technology and the Joint Quantum Institute. Very pleased to get an invitation to this talk, and I noticed that there was a let me see, master the annotation here. Flashlight, I guess. Spotlight. I noticed that it's the 2,424th meeting of the Philosophical Society of Washington. I was quite impressed by that because I guess the only way to have 2,424 meetings is to be in the business for a long time. So I went and looked it up, and sure enough, the society was founded in 1871 by none other than Joseph Henry. Here's a photograph of Joseph Henry, possibly taken by Matthew Brady, the famous Civil War photographer. And in 1873, very nearby, there was this foundational change in science occasioned by the publication of a treatise on electricity and magnetism by James Clerk Maxwell. The connections between Henry and Maxwell are quite interesting. So Henry was a notable experimentalist in electromagnetism, and indeed the unit, the Henry, is a derived unit of the system international. That's the metric system, derived unit of inductance. Maxwell was his accomplishments were in the theory of electromagnetism. That's underplaying it. What he did was to unify the understanding of electricity, magnetism, and optics, which up to that point was a completely distinct field from electricity and magnetism. And indeed, Maxwell's theory is really the first of the modern type of physics field theories. Very great influence. Furthermore, the optical vortices that I'm going to discuss this evening are actually present in Maxwell's theory. Actually, they can be seen in rather simple form. But they were not really discussed for the next 120 years because it was not clear exactly how they'd be experimentally realized. And that changed very rapidly in the 1990s and has led to a new field of science. So my themes are, first, light is a particle and wave. We'll just look at the particle and wave aspects of light and then see how light can be twisted, then to look at quantum particles as waves, because at the quantum level, there's a very strong parallelism between light and particles. And we'll see that the same things that can be done with light in terms of twisting can also be done with particles. And I will illustrate examples that have been done using the science of neutron interferometry and holography. So light. Well, anyone who's sighted has much experience with light. You're familiar with many phenomena you see in the sky and on Earth. And those have been of interest to philosophers and scientists since antiquity. And so what are the simple facts that we know about light? There's a very nice set of YouTube videos on, if you search YouTube under Newton's prism experiment, you can find them. And here we see just a white screen laid out on the table. There's a ray of white light coming across that you can see there. Now, until the end of the 19th century, virtually every experiment in optics, including the important ones we'll describe right now, were done using a light source that consisted of the sun. That becomes very important in the history of science. For example, in the discovery of radioactivity. But typically, Newton, when he did his experiments, would work in a darkened room with a pinhole in a curtain that would let light through the sun. And if you put a pinhole in a curtain, you will see the sun hit the wall on the side exactly opposite the pinhole. So we know that light travels. Simple observations tell us that light travels in straight rays. If you own property, you're actually reliant on this fact, since surveyors' lines are determined by the paths of light beams. Even the global positioning system takes it as given that light travels on a straight path. There is a small effect of gravitational curvature, but that's the greatest part of gravitational effects on the global positioning system have to do with the different speed of atomic clocks. Light is not sensibly defective. So we can characterize a ray of light with what is called a wave vector k, which is parallel to the path of the ray and which the direction of which follows the motion of light. And so what else can we can ask? We've seen the rainbow in the sky. We've seen many different colors. So we can ask the question, can we change the color of light? Is color, in some sense, an invariant characteristic? Well, I mean, there's an obvious answer, yes. Here's a simple example. We just take this white light and put it through, this is a piece of red glass, and the light turns red. You've all seen this wearing sunglasses, for example. Yes, the light changes color. Well, how does it do that? Does this red device have some property that impresses a property, some characteristic that impresses the property of redness on light? Well, Newton looked into this and found that, well, he saw something that many people had seen. You've seen it before. When you pass white light through a prism, it spreads out into a span of colors, running from red through the violet. Now, many people had seen that before, but what Newton did was he did two things. The first of which is not shown here. He put another prism in the field of a particular color. I think the example he mentions in his book on optics is in the blue. And he found that blue light entering the prism exited blue. So there was some property of the blue light that was not further dispersed by the prism. But then the most impressive follow-up to this experiment done by Newton, and as you see, this experiment just involves movement of simple optical devices about on a table in a room. Newton showed that the light could be dispersed by the white light be dispersed by the one prism and then redirected back through the second prism to become white again. So this shows directly, you can't really see it well in this figure, but it does show directly that white light is dispersed into a band of colors, all the band of colors that we see in the rainbow, and that band can be recompressed to give white light again. That second part is, I would say, of compelling intellectual importance. And furthermore, it is the basis of multiplexing of optical signals, which is critical to modern communications technology. Now, this process is active. You activate this process every time you download something on your mobile phone, not by putting prisms into motion, but by acting, by engaging interferometry in optical fibers. Okay, so there's the property of light as a ray. Now here's another phenomenon that I think all of us have seen at one time or other. A still pond with a few waves. So maybe pebbles were thrown in at one point or at another point. And you see the waves, these two waves, have the same form with respect to their origins. They look very similar. Now, so it means that you could produce a number of other waves anywhere you want in the pond, and you will still have an overall pattern of wave motion. Well, that seems a tautology. The more significant thing is that when waves, you see these two waves have passed through each other. So they collided, and when they overlap, the pattern that you see is more complicated than the original wave pattern itself. But they move, once they are no longer in the same region, they retain their same form. So this shows a phenomenon of interference. So there's a property we call superposition, which leads to the and then the fact if the water is if the pond is uniform, it doesn't matter where you start a wave, it'll look the same with respect to the starting point, and that's related to the so-called conservation momentum. Now, these two simple principles combine to make the most beautiful and useful thing in all the world: interference. Now, I will say, among people with whom I work, that is something of a moderate view. Some say that if it doesn't involve superposition and interference, it can't be of any use or interest, whatever. But let's just take the moderate view and see if we can justify that. So, first of all, this has been a tool of incredible importance. It's what Young used to do what is called the double slit experiment. It was actually a double hole experiment, 2 holes in a screen, again using the sun. And he observed a pattern of interference on the screen, which enabled him, knowing the distance between the 2 holes and the distance to the screen, you can determine the wavelength of light. So this experiment not only hinted at the wave nature of light, but indicated the size of its wavelength, which was something very small, about half a micron, 100th of a fine human hair, and corresponding to a very high frequency, a frequency of 10 to the 14th cycles per second, far higher than anyone knew of. And so Young did not know what was oscillating, only that it showed the interference pattern of the wave. Michelson, working later in 1887, which was after Maxwell had shown that light, well, what Maxwell showed was that electric and magnetic disturbances, according to his theory, traveled at the speed of light. That's highly indicative that light is a form of electromagnetism. That's been proven experimentally by many means later. In any event, Michelson built an interferometer. Well, it's different from the double slit experiment. You have a common source of light that enters and goes through a beam splitter that puts it along two paths. Those two paths recombine and are observed at the exit, and that shows an interferogram. And then to get back to the theme of telecommunications, another wonderful, useful device, widely used in quantum information, is the Mach-Zehnder interferometer, developed in the late 19th century. And this is the equivalent. This plays the role of the prism in the Newton experiment in terms of separating out and recombining signals for use in optical telecommunications. And this diagram here shows a chain of Mach-Zehnder interferometers. Each one has two inputs, which are two light beams, and then they're electro-optically controlled by an interferometer in this in the box, which takes sums and differences of the beam. It performs operations in the beam and sends it down a long stream to accomplish the multiplexing and demultiplexing operations in the network. Final example along this lines, most sensitive measurement instrument ever made, the LIGO Observatory. Well, let's see, maybe it's not so obvious. The LIGO Observatory is exactly the Michelson interferometer configuration, if you imagine this rotated on its side and laid out. Only it has a path length of several kilometers rather than of tens of centimeters. And this was the instrument. I remember the day of the press conference in early 2017. The National Science Foundation held a press conference to announce the first results from LIGO. And I was sitting in my office at the University of Maryland, tuned into this press conference, and I tried to download the paper from Physical Review Letters. And as everyone who was around then will recall, the Physical Review Letters servers were crashed by the traffic that was occasioned by the announcement of this gravitational wave. So I thought to myself, how about that? Two black holes merged like 8 billion years ago, and that has resulted in the servers of the Physical Review crashing in the year 2017. Yeah, so how important is optical multiplexing? And this will come up later in the talk, because one of the driving interests in these vortex states is to be able to use them as a new tool for increasing channel capacity, basically to do multiplexing. Well, I'll get to that later. A new form of multiplexing that doesn't depend upon wavelength, but depends upon wave front, you might say. And so I'll just say, here is this incredible network of undersea cables. Every transmission, every internet transmission between continents is handled on this vast network of optical fibers. What's not shown here, the fiber networks within countries, in most countries, are also the main trunks of internet communication. So this is something which, let's say maybe some people in the year 1990 had a dream that this could come true, but it was only subsequent technical developments that made it practical. I'd like to note that the Nobel Prize in Physics for 2014, as recently as 2014, was given for the invention of optical fiber, because optical fiber allows long-range transmission with minimal dissipation. It's not like electrical current, which necessarily has a resistive flow, or like radio waves, which are wonderful, but they diverge. The intensity of the radio wave falls off as the inverse square law. The optical fiber, there is a loss, but it can be compensated for by amplifiers placed along the chain. And we would not know the internet as we do now without optical telecommunications mediated by wavelength division multiplexing and other optical electronics. Okay, well, at last we get to the promised topic, twisting of light. So there's a beautiful experiment that was done in the Ukraine in 1990, which in my view captures in a wonderful way what it means to twist light. So it's done again with an interferometer, and you have light incident on an optical system, and this is basically a Mach-Zehnder interferometer type of configuration. One beam goes to this upper beam goes through some optics and to a glass plate, part of which is reflected into the imaging system. And this second beam here goes through a bundle of optical fibers that comes through the system, and it interferes with, this is the reference beam and the object beam in terms of holography. You're making a hologram of a bundle of fibers. And this is the pattern that they saw when the interferogram that they saw when they just literally twisted the bundle of fibers. It was a nice rectilinear bundle of optical fibers. Then they gave it a twist, and they showed that they got this interesting interferogram pattern. Now, maybe some of you recognized this when I first put it up, because it looks an awful lot like the Newton's rings pattern, first discovered by Newton's, and this is also called a Fresnel zone plate. This is an image from a book by Robert W. Wood on the Fresnel zone plate. And you see this Newton's rings or Fresnel zone plate pattern consists of islands of dark and light that correspond in the interferometry context to destructive and constructive interference. But now if you look at this, what happens when the light has been twisted, as I've just described it, you get something that looks a lot like the Newton's rings pattern out in the far field. But you see, you have one continuous island of destructive interference that winds around, and another, well, with some minor defects, another serpent of constructive interference that winds around. So you've completely changed the topology of the interferogram here, which goes from a series of disconnected regions to one continuous serpentine form. Now, what's going on there? So I'd be remiss if I didn't show the outline of an outline of the mathematics that's used to describe these vortex states, which is actually relatively simple as a matter of wave motion. So we can, anyone who wants to ask more about this at the end can ask a question, but I'll just run through it. We already talked about the wave vector K of a ray of light. And in an ordinary ray of light, we imagine it as having a smooth wave front that is perpendicular to the direction of K. And so basically, ordinary light, as we see it in the Young's double slit experiment or in the Newton prism experiment, the wave front is just a flat surface that's perpendicular to the wave vector. And this, what does it represent? It represents a region of electric and magnetic fields of constant strength. That is, if you ride at the speed of light in the direction of the wave vector on this wave front, the electric field and the magnetic field will have constant strength and direction on that field. And so that is in I'm using a Schrodinger equation here, but the answer is the same. The time derivative of the wave function, which is one of the electric fields or magnetic fields, is proportional to this Laplacian operator, which is the sum of the second derivatives of the function with respect to the space coordinates. This is a common, much of classical mathematical physics has this type of structure. The time derivative of a field is related to this Laplacian operator applied to that field. And what that Laplacian operator does is when it acts on the field, it returns the average value of the field in its immediate vicinity. And so, for example, for wave motion, wave motion is described by when the time derivative, the rate of, it's like a harmonic oscillator. The rate of change of the field is proportional to the difference from its average value. So it wants to oscillate as it propagates. For the diffusion equation, it's another matter. There's basically a diffusion. The rate of change of the time rate of change of the field is damped by something that's proportional to its difference from the average value. And so in quantum mechanics, it's much like classical wave motion. So the mathematics of the vortex states is all contained in this simple exponential function, e to the I, which is the square root of -1, times x is the spatial coordinate, k is the wave vector, and then omega is the angular frequency of light, and t is the time. And that means for a regular plane wave like this just moves along in the direction of k. Now, I believe that Dr. Daniel Lozier is in the audience, and he can, well, if there were a social hour afterwards, he'd be happy to explain to you that this solution of single oscillation in along the direction of the wave vector can be decomposed into a product of an infinite sum of a product of a so-called Bessel function along with an exponential function, which is just the sine of theta plus I times the cosine of phi. And so in other words, there are, with a coherent superposition of these type of states, you can generate the plane wave. And so the whole business of making optical vortices is how to pick out various components of this superposition and deal with them independently. So what we see here, here's what this, if you tip the wave function slightly, what you get is something that looks like the underlying plane wave along the original direction within this infinite sum of states with orbital angular momentum. That is, they have angular momentum about the axis of propagation. And the wave fronts of those waves are, so this figure A here from a very nice review article in the field by Allison Yao and Miles Paget. You see the plane waves that are associated with ordinary optical wave motion, which correspond to L equal to 0. And then you have L equal 1, 2, and 3 that correspond to a greater, increasingly greater or value of orbital angular momentum around the axis of motion. So somehow there's a form of light which propagates along an axis of motion, but its intensity rotates around it, and it leaves a hole in the center. Now, how do you? So, a state of this type was made by that optical fiber experiment, but how do you generalize it? And one very simple idea was realized early on. It's a so-called phase plate, where you just take a transparent medium like glass, and you make a wedge with a discontinuity. So the wedge has a thickness of the wedge is very small near this intersection, and the height increases. The height increases as you go around, and it reaches a maximum value of S. And that means since the phase of the optical wave changes at a different rate when it goes through a transparent medium compared to vacuum or air, which is very close to being a vacuum as far as optics is concerned, you get an overall change in phase around as you travel around the axis of propagation. And if you choose that to be an appropriate multiple of the wavelength, then you get you can generate a close to pure orbital mode of orbital angular. There's another way of describing this, may seem more intuitive to you, which is certainly useful in thinking about how do you get orbital angular momentum out of matter waves. So in other words, we know that you can make these rotating states of matter waves in which a particle is actually spiraling around an axis of its average trajectory of motion, even though there's no force acting on it. And so a useful analogy for that can be accomplished with spaghetti. I'm sure many of you have had the experience. If you make spaghetti and you only use a part of the box, you put the remaining pieces in a glass or a vase, and you see the spaghetti spreads out in this bouquet shape. There's a well-known sculpture at the Fermi National Accelerator Lab by Robert W. Wilson that exploits this principle. Was shown in the opening slide of my presentation here. This looks like a spiral motion, does it not? And even more so when you stand within it and look up. But it's made out of rectilinear beams, so that these steel beams are perfectly straight, but they are aligned so as to accomplish the apparent motion of a spiral. So in other words, a massive particle launched on one of these tubes would go in a straight line. But if you have a matter wave function, you can set it up so that the phase of the matter wave function varies around the periphery of this distant disk so that you get the coherent orbital angular motion of a massive particle. Here's a little mechanical device that illustrates that. This is a big hit on Reddit at one time, and you see what it's doing is it's moving a completely straight rod through a curved hole. So this resembles an animated action of what the Tractitious sculpture is showing us. So how is this used in practice? Well, I emphasize, what a great thing the optically based internet is. I mean, if you love telecommunications and high speed, you're having the time of your life. But it's, the reason we have a high data rate worldwide communication network is because no matter how fast it got, new uses were found for it. And so much of the experimental interest in pursuing these orbital angular momentum states of light comes from the idea that they can be used to multiplex data, just as is done with wavelength division multiplexing. So this is a inspirational example from Alan Wilner's laboratory at the University of Southern California that shows that they make these complex orbital angular momentum states, they superpose them together, propagate them, and then so they put them together on a common data line, and then they demultiplex it at the receiver end, using free space, just the open air as a data transmission medium. And they're able to get terabit per second data transmission by this form of multiplexing. Here's another application applying the same idea to to underwater ultrasound. So there are applications for communication between underwater sites that can only be done by sound because water scatters light too efficiently, whereas underwater sound can travel for long distances. The principle of sonar that's widely used. And so, however, the data rate is not high for simple underwater sound. And so again, a water wave is a form of pressure wave. It satisfies the same sort of wave equation, or a similar one to light or other media that are described by Laplacian. And so it also, the sound waves in water also have this vortex character that can be used. You can take the angular momentum of the water waves and use it as a discrete variable in order to further multiplex communications. Here's another more recent publication on the development of a vortex micromaser to serve as the source of polarized of vortex light for these sorts of applications. And there's another absolutely crazy one. The figure seems to have gone lost, but my collaborators at the University of Waterloo have shown by an experiment on human vision that the human eye can discriminate these vortex states of light. And so they're working with ophthalmologists at the medical school at Waterloo to see whether this can be whether this index of discriminations, multiplexing, can be used as a form of for vision correction or for diagnosis of medical condition. ocular medical conditions. There's two, I'll just point out two recent reviews of this field, very well written, widely accessible. One in the membership magazine of the Optical Society of America. And then there are two articles published about 3 years old now on this. This field has become known with under the name of structured waves of matter and light. So that is studying and exploiting what you can do with changing the wave fronts of optical or particle motion. And there's developments in many areas. And I'll just give you an outline of what that means in general, and then show you how we've used it in the context of neutron interferometry. So I gave you a picture of an interferometer, the Michelson and the Mach-Zehnder interferometer. And if I was asked to explain them, or the Newton's double slit, we'd say, well, we have a wave that comes through this hole, and it forms a wave motion on this screen. And then another wave comes through this hole. It forms another wave motion on this screen. And you see the interference pattern, just like you'd see as if on that pond, we had waves emanating from two different points, and we saw a complex interference pattern along a ray along a plane where those two waves overlap. When you talk about particles, on the other hand, it's a little bit it's a little bit hard to express the phenomenon in such simple terms. Because if you think of a particle, which, by the way, when we're talking about a particle, we mean single particles of light, or like I'll show you in the next section, neutrons, which are definitely discrete objects that are detected one at a time. Each particle is detected by a discrete click. And so if you were sending particles through double slits, if a particle go through slit 1, it was going to hit the screen. And a particle that's going through hole 2, well, it might also hit the screen, but the fact of the interference phenomenon seen by Young for waves has both a constructive and a destructive part. So when the wave from 1 and the wave from 2 interfere constructively with the same phase, the amplitude of the wave is twice as big as it would be from either wave alone. When they interfere destructively, then the waves cancel. So how, just to put it in the crudest way, how could opening up a second slit in this screen cause the detection of particles to decrease? By the way, these are non-interacting particles, so they don't scatter from each other. So it's a real mystery, and we'll resolve that in a moment. And even Feynman, well, we won't resolve it. We'll just explain how it works. Not why it's that way. And Feynman has expressed this as the only mystery that is in the heart of quantum mechanics and reality, contains the only mystery. So there's a famous New Yorker cartoon that expresses this paradox in a visual sense. How can an object how can a projectile take two paths around an object? And we'll just again see how that works for the case of neutrons. So the experiments I'm about to describe to you were performed at the the NIST Center for Neutron Research on the campus of the National Institute of Standards and Technology at the University of Maryland. It's a 20 megawatt thermal research reactor that has a this containment building here shows the reactor, and then there's a guide hall here in which experiments are done with cold neutrons that are emitted by the reactor. So you might think of in an optical sense, the reactor is basically a source of light, and then there are light pipes that carry the light down to optical experiments in this beam hall, though the light consists of massive neutron particles. The neutron was not created just for our use in interferometry. It's an essential constituent of every nucleus of the periodic. Every nucleus that we know has neutrons in it, except for the bare nucleus of hydrogen. And it's sort of a partner to the proton. It's about the same mass as the proton, but it has no electric charge. And that's very important from the standpoint of its ability to penetrate matter. So this is a wonderful vignette, two photographs, or an optical photograph and a neutron radiograph, which is the neutron equivalent photograph taken by my colleague Dan Hussey at NIST. On the left side, you see these two Asiatic lilies sitting in a lead cask. This lead cask is used to transport radioactive materials because lead absorbs X-rays and gamma rays very efficiently. And on the right, you see exactly the same object, but now it's been rotated. So you're seeing it's standing on its foot, which is at the bottom of the cask here, standing upright. And neutrons are streaming through. They go right through the lead cask, but they scatter, as you can see, from the veins in the leaves. And I think you should be able to see it, the stamens and the pistils of within a blossom of this delicate flower inside a lead cask. Now, how is that even possible? Well, it's because the neutrons interact with other nuclei only through the strong interaction. There is a magnetic interaction that's possible, but it's not relevant when matter is non-magnetic. And that means a neutron doesn't interact with the electrons in the material, which is the usual thing when a charged particle enters matter. Its force accelerates the electrons. If it's very energetic, it just creates a shower of electrons within the material. Its energy is dissipated very rapidly. The neutron is basically almost like an elastic scattering element, but it simply has a larger scattering cross-section for hydrogen than it does for lead. And what you're seeing here, this imaging here, what it's showing you is that the concentration of water, which is the chemical compound H2O, two hydrogen atoms, one oxygen atom, water is concentrated in the veins and in the internal structures of the blossom. Otherwise, the neutron behaves in cases like this much like light does in the material, except it has a very small index of refraction. So index of refraction for a neutron in a neutron transparent material is 1 plus or minus a part in a million, versus index of refraction for light is 3/2, 1 plus a half. So the this is another way of describing the near, the transparency of materials. Oh, just for a famous relation, the rule of twos, the neutrons coming out of a reactor have a speed of 2 kilometers per second, kinetic energy of 20 millielectron volts. And I guess the most important point from the standpoint of this discussion, they have a very short wavelength, a wavelength of 2 angstrom units. I'm quoting this from the original source. In modern terminology, we'd say it's 0.2 nanometers, 0.2 of a nanometer. Well, the wavelength of red light is about 500 nanometers. So these thermal neutrons have a wavelength that's 1,000 times smaller than the wavelength of light. And it's also comparable to that wavelength is comparable to the distance between atoms in condensed matter. So this means that neutrons are used as a very good tool for understanding the structure, crystalline structure materials, and also for understanding energetic phenomena that occur at these sorts of energies. So neutron interferometry was developed by a number of people, but perhaps the most notable people in recent times are Helmut Rauch and Sam Werner, who authored a second edition of a monograph on the subject published 5 years ago. And Werner was a member of a team that used this interferometer to do the first measurement of the effective gravity on a quantum particle. A very profound experiment. And how it works, this is the Mach-Zehnder configuration that we described in the earlier part of the talk, widely used in optics. A neutron comes from a nuclear reactor. What you're seeing here is a started life as a cylindrical dowel of ultra pure silicon with it's about the size of a 12-ounce soft drink can, as you can see from this ruler. And then it was milled into this shape. So that original cylinder, much of it was cut away to give these three planes, and a neutron entering from the reactor incident on this plane. Part of it is just transmitted in the same direction. Part of it is Bragg diffracted by the crystals in the plane to the next mirror. And then when this original beam hits the second plane, part of it is Bragg diffracted, and just as in the first instance, half of it is transmitted, but it goes outside the interferometer, so it's not detected again. And you have the same thing applies for this beam originally coming from Bragg diffraction. Part of it goes right through and is lost, but about half of it is Bragg diffracted again. And these two beams recombine on another beam splitter, and then you get the sum and the difference in some sense of the two beams into two detectors on the output channels. So this is basically a way of seeing that matter waves have a phase, because, well, let's just see how that's done. Here's a schematic of that detector frame as seen from above. The incident beam, the first beam splitter, the second pair of beam splitters, which actually serve as mirrors here, and then a final beam splitter in which the two beams recombine. And so there is a so-called phase flag, which is just a slab of pure quartz or something like that, or another material sample. And in this case, the phase flag is rotated. Is rotated. The independent variable here is the rotation angle of the phase flag, so that when it's rotated, the quantity of material in the phase flag that the green beam has to pass through changes, whereas it doesn't affect the red path. And then if you look at the output of these two neutron detectors, you see, certain phase flag, almost all the neutrons are found in the H, and then as you vary the phase flag, you see this oscillation back and forth, where the number of counts that are seen in each detector are very sinusoidally. these, you can see here, you see the error bars on this data. Each one of these data points, well, a data point up here represents about 2,000 counts. That means the H-beam detector has counted 2,000 neutrons. Each one enters the detector and registers a discrete count. And virtually never does more than one neutron enter the H detector. And we know that because this is the sum of the accumulated counts. There's also, these are accumulated during an interval of time. And we can see from the pattern of the random counts in that interval that at the time the 1,999th neutron was detected, the 2,000th neutron detected had not even been born in the reactor yet. That is, there was not enough time for it to leave the reactor to overlap with the previous count. So this really illustrates how it works, that when you use a quantum particle source, like a neutron beam in an interferometer, you get exactly the same results you would get for waves of light. Another configuration. So we decided to try experiments that would apply some of the ideas of twisted light to neutron beams. Once again, using a phase plate. Here's a drawing of the phase plate, where you basically, it's like a winding staircase. Here's the top of the staircase, and you walk around the staircase. You've gone down one floor, and you just want to make the distance between floors be an integral multiple of the neutron wavelength in order to get the constructive interference that we seek. And so here's actually, I've looked at actual spiral staircases. They tend to have the same geometry. That is, if you go between floors if you go from an upper floor to a lower floor on a spiral staircase, you'll usually find that the direction that you're going when you enter the top floor of the spiral staircase is the same as the one that you exit when you get to the bottom. So we, in order to put quantized magnitudes of angular momentum into the neutron beam, you have to tailor these phase plates so that the step size is the same value, and that you do multiple winds around you change the step size so that you get an appropriate integral multiple of the critical step size. So we made a number of these plates that were calibrated to give unit changes in angular momentum, and we use them in the Mach-Zehnder configuration of the neutron beam. And here's the results are a little bit noisy, but we show the interferogram for L equal 1, 2, 4, 7.5. The results are in accordance with what one expects from the simple picture of transferring angular momentum to the neutron waves. Now, for the people who thought about this problem already, I'll say that in the case of neutrons, we have only a partially coherent neutron source. So we don't have a pure a wave of pure angular momentum entering this phase plate. In fact, it consists of an admixture of millions of angular momenta, independent angular momenta, but each one interferes with itself so as to give rise to the pattern that you see. So we're not producing the vortex state, but we're demonstrating transfer of quantized angular momentum to the neutron. Now here's a configuration we do addition 1 plus 2. So the interferograms for magnitude 1 and magnitude neutron. We just put the 2 phase steps back to back, and we see that 1 plus 2 is equal to 3. That's not the first time that's been discovered. We've used this to record a hologram, much like, so this pattern looks much like the hologram that the Ukrainians computed for their optical diffraction pattern. And we found it using basically just a spatially resolved single phase plate with a prism that serves to do a linear spread of the neutron beam across the digital camera. This was and is noted, as a physics newsmaker 4 years ago. First, LIGO got the first prize. No surprise there. And we have since looked into multiplexing these phase plate assemblies by using magnetic fields. So this shows an optical implementation of a means of making a lattice that would give it rise to a pattern, a rectangular pattern of neutron beams with orbital angular momentum. And that has been implemented. We have first implementation within the laboratory during the past year. So this is a challenging and fascinating field of neutron physics, which we got our inspiration from all the work in optics and other wave motion, and I think it will continue to. It's an attempt to program the wavefront of a neutron beam, much as you can do for a beam of electrons or light, and we'll just see where it goes. So I'd like to conclude by thanking my number of collaborators, many from NIST, many from the Institute for Quantum Computing at the University of Waterloo, headed by David Corey and Dmitry Pushin, and the operational radiation safety staff of the NIST Center for Neutron Research, which keep our operations safe and productive. So that's my story for tonight. I'll stop sharing my screen.
Well, thank you, Charles, for that very interesting and technically rich discussion. We have time for questions. Zoom participants who want to ask a question should raise their Zoom hand. And when we call on you, we'll unmute you and you can ask your question directly. If you don't have a microphone, you can also submit questions in the Zoom Q&A panel. YouTube viewers, text your questions in the YouTube chat box. Text questions will be read aloud for everybody to hear. So we can start with a question that was asked relatively early on by Richard Garwin, who asks, in the interference of pond waves, why is the wavelength increasing with the distance from the origin of the rings?
One always takes one's, let me see, can I share this? I'm sorry, I've done something wrong here. I'm just trying to go back to that screen. Can I be given control of the?
Yes, I'm not sharing, so you can share. You have to hit your share screen.
So I can. So let's go back and look at the tape. Oops. Yes, I mean, I see, well, let's see. I see that these waves um, the wavelength is increasing. Uh, I suppose that it's because they're coming near the shore, and so the dispersion relation for water waves varies with depth. So this example presumably would be a little bit more convincing in a deep ocean rather than the pond that we see here. Is that correct, Dr. Garwin?
We can, if you have a microphone, Richard, you can answer directly, but you can also type it in as a question, kind of, in the Q&A. And while we're waiting for that, maybe we'll take a question from Carrie Liss, a fellow astronomer. Carrie?
So, oh yes, I actually just typed my question in the question and answer. So I know enough physics, quantum physics, to get in trouble. I'm an astrophysicist by trade. And one of the things I've been fascinated about with the Higgs discovery is that if the Higgs field is a scalar field, it could act like an ether. So one of the ways to test whether there is such a, if you will, a modern ether would be to do a interferometry experiment with massive particles that couple to the Higgs, unlike the photon, which doesn't. So could you do your neutron interferometry experiment and then rotate it parallel and perpendicular to the Earth's motion around the sun and try to do a modern day Michelson-Morley experiment with neutrons?
Oh, well, that is a very good question. And in fact, Michelson-Morley experiments have been done with neutrons.
Ah, what are the results then? I'm out of touch.
So in fact, the Earth's rotation is measurement, or let's say Sagnac interferometry has been done with neutrons to measure the Earth's rotation. And it's even impossible to use it.
Okay, I'm speaking. Is it hearing me?
As a neutron, as a moon detector. So the moon comes over the horizon. The change in tides, massive tides, can be observed with neutron interferometry due to the change in mass. So this book by Sam Werner and Helmut Rauch that I cited, published called Neutron Interferometry, published by Oxford University Press in 2015, is a great resource for seeing what has been done. So yeah, a lot of these fundamental challenges. For example, just the question of how does gravity act on a quantum particle?
Yes.
I mean, let's just say this: gravity stands outside all the rest of physics, and so how it affects the motion of something governed by quantum mechanics, you might say that's not the most challenging test of quantum gravity, but it is a test. And it turns out that to within experimental uncertainties, actually, there's a little bit of debate about this, but it seems like there's not much difference between, it's debatable whether there's a difference of the effect of a gravitational field on a quantum particle that's different from just the effect of a linear potential. So in the Earth's gravity, the universality of free fall is equivalent to a linear potential for a non-relativistic quantum particle, and the de Broglie interference experiment conducted by neutron interferometry yields a result that I think is consistent with that.
And it's similar to what if you were to put a potential around a superconducting Josephson ring, and you can see actually you can modulate the phase. So you can do the same thing. Gravity does the same thing; it modulates the phase.
Yeah, indeed. Well, there's something called the Aharonov-Kasher effect.
Thank you.
Which has also been it's using an electric field rather than gravitational field. But
Yes.
that has also been checked with neutron interferometry. But I'm not the person to talk about that, and I will just refer. Actually, this book, I think Sam Werner would like me to let you know it can be bought on the Kindle, but it's certainly, if you have a interlibrary loan available, it's it's the definitive reference for all these sorts of.
I work at the Johns Hopkins Applied Physics
If we were having if we were having a social hour, I'd say save it for the social hour.
Right, sorry.
Let me go on. Richard Garvin is on the line, and he's got a. I think he has an answer. Basically, I think he's.
So if you look at the pond, you see that it's symmetrical in all directions. The wavelength increases with distance, not only on the left, but on the right rings. But so neither of us understands that, I think.
Well, I'm in good company then.
Yeah, but now speaking of LIGO, the most recent detection was from 8 billion light years, but the original one was much closer. It's just a detail. But a question of your talk, is the orbiting angular momentum multiplexing actually in use through telecommunication fibers?
I'm sorry. Overlay.
Is it actually used for multiplexing through telecommunication fibers, through optical fibers?
Yes. So I gave a reference to a paper by Alan Wilner, Willner, who's sort of the master of this at the University of Southern California. So yeah, at the present time, the technique is to the best of my knowledge, restricted to free space implementation. So those results that I described were for basically transmission of light through air. And, there in a fiber, there's a, you'd also get quantized angular momentum, but of course those propagate at very different speeds. So the advantages aren't retained in fiber. So I think the multiplexing, both for the electromagnetic and the acoustic applications that I've mentioned, it's been demonstrated only in free space propagation.
Thank you.
I will say I was reading in looking up exams for this talk, I was reading papers in the wireless communications literature. And I think we all know about 5G. So 5G is coming, 5G is coming, whatever that may be. But there's a bunch of literature on what 6G might be. And so 6G is even wilder and crazier than 5G. And there's in the Internet of Things world, there's a much greater role for free space optical communication than there is in our conventional world. And there are some speculations about how you might make OAM transponders for the Internet of Things to deal with the channel capacity of 6G when it comes. But I think that's speculative.
Next question will be from Joel Wilson. Joel, hello.
Hi, Professor. I just typed my question, but since you're talking about interferometry, any thought of using holograms to further analyze vortice phenomena? It may not work, but
well, yeah, certainly. I showed what we believe is the the equivalent, realized with the neutron interferometer of the classic hologram. It's an interferogram, and so what we have not done is to take that photoelectric image and then illuminate it with light to see the step profile of the faceplate.
right.
But a computational simulation of that step shows that there's a noisy image that you get. But so the holograms that we get from the neutron holograms of objects that we make look like they could reproduce crudely the three-dimensional form of that object, if illuminated with light. I think the noise level is still too high.
Prohibitive.
This is not going to be a practical means of microstructure analysis.
Right. Thank you.
A question from Sarah Heap. Her question is, have you looked into the vector vortex coronagraph, which has great promise to detect exoplanets orbiting a star. Sorry, we lost it just a second.
Are you reading from the?
Great promise to detect exoplanets orbiting a star 10 to the 10 brighter.
Uh,
I can't point right, but I think she
sorry,
wants to know whether.
what was the name of that instrument again, Larry?
Hmm?
What was the name of that instrument again?
Vector vortex coronagraph.
Well, I'll make a note of it. So no, I don't know of that.
We have a question from.
And I will say hello to, as I believe I call her, Sally Heap. It's nice to hear from you again. I was last at NASA Goddard Space Flight Center probably about a year ago.
Small world. We have a question from YouTube chat, and that is, can you talk about your work with Bose-Einstein condensates and whether there's any relationship between this work and that work?
Bose-Einstein condensates. I guess there is a relationship between this work and the use of Bose-Einstein condensates for matter wave interferometry, but it's not that strong a relationship. The Bose-Einstein condensate is to a quantum gas much like what a laser is to a light bulb. So an ordinary gas of particles has these random velocities, thermally distributed. And in the Bose-Einstein condensate, you have all atoms, well, they can all be made to be moving in the same direction. That's like a laser puts all its light in one direction, whereas a light bulb spreads it out. So a Bose-Einstein condensate is a great source for doing experiments on atom interferometry. That is, and those have been done, again, using these Mach-Singer type configurations to see interference between atoms going through an interferometer. So in the sense that what we're doing is a form of matter wave interferometry, it does have overlap with atom interferometry, and we've actually learned valuable lessons from atom interferometry in terms of like building decoherence-free subspace configurations for neutrons. But as a practical matter, the experiments are vastly different. In fact, atoms have the greater power as an interferometric tool at the present time, and they may have it forever. What neutrons give you is the power to maintain quantum coherence in the neutron as it transits, a 10-inch thick sheet of lead. That's something no atom will ever be able to do. So we're thinking about, we actually have been designing, not me, but some of my collaborators have been designing experiments to measure the Newtonian gravitational constant by neutron interferometry, which that would be an extension of what has been done with an atom interferometer.
We have one comment. I don't think this completely explains it, but the comment is a vortex coronagraph is a type of optical instrument which enables the imaging of very faint objects near very bright objects that would normally be obscured by glare. It tells us what it does, but not necessarily how it works.
Okay, well, I've taken a note of it, and I will look it up.
So I think that seems to wrap it up. No more questions coming in. So,
Well, thank you all for
Charles, for
here.
generously sharing your time with PSW
My
and
pleasure.
giving this very informative lecture and having enjoyable back and forth with some of our questioners.
Thank you so much.
We don't have an audience to applaud you, so I'm going to do it for them. Been great. Before the audience goes, there are a few important notes. Won't take long. Hang on to your screens. And the fall lecture series has been posted to the PSW website. The next speaker will be Davey Smith, and his lecture will be on COVID-19 treatments and trials. Davey is involved in running several clinical trials involving potential treatments for C19. He is chief of the Division of Infectious Diseases and Global Public Health at UC San Diego, where he also has a number of other roles. Please join us for Davey's talk on Zoom and YouTube. Before we go, let's thank tonight's crew, James, Robin, Ann, doing our chat. Thank you very much for making this possible and helping it to go as smoothly as it has. I now adjourn the meeting, the 2424th meeting of the Society. I wish everyone a good evening. The meeting is adjourned.